In this video, we are going to build a universal procedural mirror ball generator in geometry nodes. We'll set the radius, tile size, add a little rope loop on top, and you'll have a fully procedural Christmas ornament that you can drop straight into your holiday scenes. Let's start with a simple sphere. I create an icosphere and immediately expose its radius to the group input of the geometry nodes modifier. I set a minimum value, for example 0.1, and make it single, so there is one radius value for the entire ball. Next, we need to instance planes onto the sphere. These will be our mirror tiles. I create a grid, and in the group input, I add a parameter called tile size. This is the size of the squares. By default, we'll set it to 0.1, with a minimum of 0.01, also single. The first problem we run into is that all planes are pointing upwards. We need each plane to hug the sphere, with its local z-axis aligned to the sphere's normal, and the second axis lying along the tangent of the surface. For this, we use the axis to rotation node. For the primary axis, we use the surface normal of the sphere. We want the local z-axis of the plane to look along the normal. We get the secondary axis via a cross product, so that it's perpendicular to both the normal and the z-axis. We plug the result of axis to rotation into instance on points rotation input. Now each little square sits nicely on the sphere. So we already have a working base setup, a sphere, and planes distributed over it. But there's an important problem. If we change the sphere radius or the tile size, the number of tiles does not change. The squares either start intersecting or we get huge gaps. We want different behavior. If we increase the radius, we get more tiles. If we increase the tile size, we get fewer tiles. But the sphere radius stays the same. For that, we don't just want to instance squares on vertices. We first want to create rings and place our planes along those rings. Let's create the points where we later place the mirrors. We take the arc primitive, a curve arc. We're interested in a half circle, so we set the angle so that the arc is exactly half of a full circle. We rotate it so that it's aligned along the z-axis, so the half circle goes from the bottom of the sphere to the top. We connect the radius of the arc to our sphere radius. Now the question, into how many segments do we divide the arc? We already have the sphere radius and the desired tile height along the vertical tile size. The circumference formula is 2 pi r, so the length of the half circle is pi r. That means the number of segments along the half circle is the length of the half circle divided by the tile size. Since count must be an integer, we use float to integer in floor mode. Now we have an arc with the correct number of segments. The next step is to turn the points of this arc into rings. We instance a curved circle on each vertex of the arc. This gives us a set of rings arranged along a meridian. We see right away is that the circles are not centered in the way we'd like, and the coordinates don't behave as we need. We'd like the z of the arc to control the vertical position of the rings, and the y of the arc to control their radius. We use a set position to place the rings. But if we now try to take y as the radius, we'll get 0 everywhere, because after set position the y component has already been zeroed out. So before set position we use capture attribute and grab the original y attribute. Then we feed this captured value into the scale input of the instance on points node. Now we need to resample each circle independently to get points for each tile. If we want a different number of points on each ring, we first need to realize instances, so that each circle becomes a real separate curve, and only then apply resample curve. To compute how many divisions we need around each circle, we use the same circumference formula, 2 pi r divided by the tile width tile size. But now the radius of each ring is different, so instead of using a fixed radius we can take the spline length of each circle. That gives us the circumference directly. At the beginning this wouldn't have worked, because we would get a dependency loop. The arc length wasn't defined yet. But now the radii are already defined, and we can safely use this node. Now we plug the new points, the result of resampling the rings into our old part where we were instancing the planes. Overall it looks good, but there's a new issue. The rotation is wrong. This happens because the normals of our curves don't match the normals of the sphere. Since we ultimately just want a sphere, we don't need to fight with curved normals. Instead, we just take the normalized position of each point. Position normalize. This becomes the normal vector from the center of the sphere pointing outwards. We plug this vector into axis to rotation, just like before, and all tiles line up correctly on the sphere again. Now let's add a material. We create a new material and call it, for example, mirror. We make it metallic and lower roughness to a very small value. I usually copy these settings to the viewport shader as well, so I can see the final result directly in the working view. Another important point is the gaps between the tiles. Right now they sit flush and visually stick together. To add gaps, when we compute length for resampling, we introduce a small multiplier, which we'll call epsilon. By default, epsilon equals 1.01. This means we slightly increase the length we divide by, and the squares start to spread apart. We add epsilon to the modifier parameters. We take epsilon into account in the resample calculations, and we get nice, even gaps. Right now the tiles are still see-through because there's nothing underneath them. Let's add a base. Our original icosphere is perfect for that. We take the same sphere we used at the start, but divide its radius by epsilon so that the base is slightly smaller and doesn't poke out. We create a second material for it. A simple black diffuse, very dark. For example, 6,000 in brightness. Don't forget to assign the correct materials to the instances and to the base. We join the base sphere with the tile instances. And now nothing is see-through anymore. We're almost done. One detail left. If we now start increasing the tile size, at some point the seam around the ring will line up exactly with the center of a tile. This doesn't always look good. The seams become too noticeable. To fix this, let's give ourselves control over the rotation of each ring. We want to rotate instances globally, not locally, and we want all instances at the same Z level to share the same rotation. To do this, we take position and extract the Z component. Based on Z, we compute a rotation offset. We can simply multiply position Z by a coefficient. We simply call this angle with a default of 0, type angle, mode single. Then we feed this into combine XYZ in the Z slot and plug it into the rotation input of the rotate instance node. Now we can slightly twist individual bands of tiles and pick a nicer pattern so the seams don't jump out. Now, let's turn our mirror ball into a Christmas ornament with a little loop on top. We create a UV sphere and expose its radius in the group input. We call it root radius, shape single. We create a curve line, place it in the center along X or Y, and give it a very small length. Then we add resampled curve with count equals 3. We take set position. Using index equal 1, we select the middle point. We use combine XYZ in offset to move this point up along Z. By default, let's use half a meter. We expose this to the group input and call it rope height. Then we use set spline type in Bezier mode. And set handle type in the default smooth mode. We get a little loop. Into curve to mesh, we plug a curve circle. Radius by default is 100. We expose it and call it rope radius. We join this with the root sphere, and then move it up along Z by the radius of the mirror ball. We join it with the rest of the geometry. And the ornament is ready. Thank you for watching until the end. This is the procedural mirror ball we ended up with. With just a couple of parameters, it turns from a disco ball into a Christmas ornament. You can drop straight into your holiday scenes. If you'd like to see more in this mini-series, let me know in the comments whether you'd be interested in a video about a procedurally animated branch for this ornament in geometry nodes, or a procedurally imperfect mirror, or maybe a partially procedural world shader with flickering colored lights. Or suggest your own idea for the next small holiday asset we could build procedurally. And if you try this setup yourself, feel free to send me your results on Instagram. I'd really love to see what you come up with.